Welcome back to the first talk of the semester. Today's speaker is Megan Mansfield. Megan received PhD at University of Chicago. And then we have her here as a NASA second fellow, and then also an Alien Earth team member. So,
yeah, awesome, thanks. So today I'm going to be spending most of my talk telling you a little bit about a method I've been developing to look for atmospheres on terrestrial planets orbiting M-dwarfs with JWST. But before we go right into that, I'm also going to give kind of a bit of an overview of like the greatest hits of exoplanets in the first 6 months of JWST. Whoops. There we go. Okay, so I always like to give this introduction at the beginning. A lot of people here are probably like all up to date with why exoplanet atmospheres are interesting and how we study them, but just in case anyone doesn't think about exoplanet stuff a lot, I'm interested in studying exoplanet atmospheres kind of for two big reasons. The first is that we can use observations of their compositions to try and understand how these planets formed and evolved. And then the second is that we can measure their thermal structures to understand a little more about how different physical processes operate in planetary atmospheres. So of course, if we want to study that in gas giants in particular, we have a few great examples in our own solar system that we can extensively study. So we've sent probes like Juno to Jupiter, which captured this photo. And we've also studied Saturn extensively. This photo is from Cassini. But if you're interested in understanding planet formation in the solar system, that's basically all we get when we're talking about gas giants. We have two instances of formation of a gas giant around a single star. But if we broaden our horizons and kind of consider the whole population of exoplanets, we know of thousands of exoplanets now orbiting thousands of different stars. So we can really kind of use this broader sample of exoplanets to understand a little more on like a larger Milky Way scale how planet formation happens. And so this is just kind of showing again that not only do we get this broader scale of understanding planet formation with exoplanets, but we can also probe populations that we don't have access to in our own solar system. So this plot is showing all of the known exoplanets with the period on the x-axis and their mass on the y-axis. And the red letters there indicate our solar system planets, Earth, Venus, Jupiter, and Saturn. And so the exoplanets that we've mostly detected really probe different regimes from the planets we have in our solar system. We've detected lots of very hot planets, much more close in than our own solar system planets. And we've also detected planets at intermediate size ranges, like things in between the size of Earth and Neptune, which we don't have any of in our own solar system. So by looking at these exoplanets, we can kind of get this bigger understanding of what's going on in the universe outside of just our own solar system. So again, this will probably be a review for everyone, but I really want to quickly go through this just so I'm not leaving anyone behind. So there's kind of three main ways we study the atmospheres of transiting exoplanets. The first is in primary transit, when the planet's in front of the star from our perspective. So when we see the planet from that perspective, then we can see starlight getting filtered through the planet's atmosphere, and we can use that to measure the composition of the atmosphere by looking at molecular absorption features from different things in its atmosphere. The second is secondary eclipse, where the planet is behind the star from our perspective, and in that case we're measuring thermal emission coming from the day side of the planet. So we can use that emission to measure both the planet's composition, again by looking for molecular features, but also the temperature pressure profile of the planet's atmosphere. And then finally, there's phase curves where we, again, measure thermal emission, but in this case, during a full orbit of the planet. So all the planets I'm going to be talking about today are close in enough that we assume that they're tidally locked, which means that they have one permanent day side facing the star and one permanent night side facing away from the star. So in that case, when you observe a phase curve, what you're effectively measuring is thermal emission as a function of longitude on the planet as it rotates. Okay, so as I'm sure you're all aware, JWST launched successfully, finally, in December of 2021. And after several months of commissioning, it started sending down data just this past July. And in those few months that we've had JWST, only a little more than 6 months now, it's already revolutionizing our understanding of exoplanet atmospheres. So I'm going to give some quick overview of results from this program called the Transiting Exoplanet Early Release Science Program. So this was part of a set of programs that were put together by Space Telescope to use JWST to produce early science in a wide variety of different scientific areas. And the idea with these early release science programs was that they would first obviously give some interesting science results, but also that they would kind of test out the different instruments on JWST and produce a guide for the community as to how to use these instruments to best achieve your science goals. So the Transiting Exoplanet Early Release Science Program in particular consisted of 3 different parts. The first one was a transmission spectrum of WASP-39b, which was observed last summer in July and August. So this was a transmission spectrum spanning a broad wavelength range from about 0.8 to 5 microns. And that was done by combining observations from 4 different filters on 3 of the different instruments on JWST. And as you can see, if you look at this plot, this has simulated data for those observations. Several of those different filters had overlapping wavelength ranges. So the idea for part of this program, part of the goal was to figure out how well you can combine transit observations at different epochs with JWST. So if you want to build up something like this broad panchromatic wavelength transmission spectrum of a planet, how well can you be confident that if you observe with one instrument at an earlier time and one instrument at a later time, that you can piece together those data sets without having to worry too much about instrumental offsets. The second part of this program was an emission spectrum of WASP-18b, which was also observed last August. The goals of this program were mostly to test out how well the instruments on JWST can do in the limit of observing the brightest things they can look at. So WASP-18, the star, is a very bright exoplanet host. So the idea here was to see how well the instrument works when looking at these really bright exoplanet host stars. And then finally, the last piece of this program, which was just observed in December, so I'm not going to be talking about it much today because it's still kind of in progress, was a phase curve of WASP-43b. And this part of the program was kind of designed to see, for phase curves, you generally have to stare at the target continuously for 1 day up to a few days long. So the idea with this part was to see how well JWST can stay stable on a single target when observing for these really long baselines you need for phase curves. All right, so I'm just going to give a brief summary of what we found for WASP-39b with that transmission spectrum program. So like I said, this was a transmission spectrum pieced together from 4 different instruments on the telescope. The first is nearest SOS, and here I'm showing the transmission spectrum from that part of the observation. And you can see that we detected potassium, water, and carbon monoxide in the planet's atmosphere. So then the second part of this was a transmission spectrum with NIRCam. And for this one, we again detected water and also importantly showed a non-detection of methane in the planet's atmosphere, which I'll come back to in a bit. So then next we looked at it with NIRSpec's G395H filter, which again we saw water, CO, carbon dioxide, as well as sulfur dioxide, which I'll also talk a little bit about later. And then finally the NIRSpec prism mode, which is kind of a lower resolution mode spanning almost this entire wavelength range and confirmed most of those other detections that we'd gotten from some of those other modes. So combining these 4 observations of this one hot Jupiter, we really detected a ton more molecules than what we had the ability to see on hot Jupiters before. So previously, the state of the art in observing hot Jupiters was to use the Hubble Space Telescope. And when you look at a hot Jupiter with Hubble, because of the limited wavelength range Hubble was sensitive to, regularly water was detected on these planets. Sometimes if you went to slightly shorter wavelengths, there would be detections of sodium or potassium. But that's basically it. That's all the information we had on this entire population of planets. Now, with just the first JWST dataset we've looked at, we've confirmed all these previous detections. We see water, we see sodium, we see potassium. We've also detected carbon chemistry on this planet, so we've detected resolved features of CO and CO2, and as I said before, we placed a really tight upper limit on the presence of methane in the planet's atmosphere because we didn't detect methane. And combining those, we think this planet might have a low C/O ratio, although the group is still doing some more extensive modeling to get like real error bars for that atmospheric measurement. We also found evidence of patchy clouds on this planet. So it turned out for the short wavelength observations, they weren't well matched by a model for a clear atmosphere, but they also weren't well matched by a model for a fully cloudy atmosphere. So what we think we're seeing on this planet is that it has some patches of clouds and some patches of cloud-free atmosphere, which are combining to produce the transition spectrum we see. And then finally, there was that detection of SO2, which this is the first time we've detected sulfur chemistry on an exoplanet. And this is also the first time we've made a direct detection of photochemistry in an exoplanet's atmosphere. So the reason this is a detection of photochemistry, this chart kind of shows how this works, but essentially in the atmosphere of a hot Jupiter, you would expect there to be water and hydrogen sulfide. And then when light from the star interacts with that water and hydrogen sulfide and breaks apart those molecules, that process kind of at the end produces sulfur dioxide, which is what we were able to detect. And we wouldn't expect to see high levels of SO2 in the planet's atmosphere if there wasn't this active photochemical process going on. So this was the first time that we've ever seen for a planet outside the solar system this active photochemistry, which we see on several planets in the solar system as well. So just from observing this single hot Jupiter, we can already see how JWST is really going to change our understanding of hot Jupiter chemistry. So one way I'm showing this is this plot right here. I'm showing different ratios of different elements for all of the planets that we've ever looked at before. On the top left here is the oxygen abundance relative to the star's oxygen abundance. The top right is the same for carbon abundance. The bottom left is showing what I'm calling net volatile abundance, which is combined oxygen and carbon abundance relative to the star. And then on the bottom right is the C/O ratio, and all of these are shown relative to the with the planet's mass on the x-axis. So before we had JWST, when we were observing planets mostly with HST, we were only able to observe water. So we really only could measure oxygen abundances. So that's all of the gray points in that top left plot. On the other hand, with our own solar system planets, we have very good measurements of carbon abundances from methane in their atmospheres, but we actually have a hard time measuring oxygen in our own solar system. And that's because the solar system gas giants and ice giants are so cold that oxygen begins to condense out of their atmospheres. So it's very difficult for us to remotely measure it, and we only have a solid oxygen abundance for Jupiter, where we actually dropped probes into its atmosphere from Galileo and then from Juno. So for the exoplanet population that we'd observed before JWST, we could measure oxygen really well, but not carbon. And for the solar system, we can measure carbon really well, but not oxygen. You'll see in the background here as well a couple tan points. Those are a couple high-resolution observations of exoplanets, which also can measure both oxygen and carbon. But these red stars here are showing our first estimates for WASP-39b as observed with JWST. So really, JWST is going to give us one of the first chances to measure precise oxygen and carbon abundances on these planets and really understand more their volatile chemistry, things like the carbon to oxygen ratio, from which we can try and understand a bit more about how these planets formed.
Hey, Meg.
Yeah.
I'm really confused about the error bars for Jupiter.
Yeah. Are you confused because they're so much bigger than
Well, I'm confused because you said you couldn't measure oxygen except from a probe. So I was expecting the Jupiter point in the O to O star plot to also be extraordinarily large, but then it's not.
Okay, yeah, so, well, okay, so there's kind of, I guess, a couple things here. So the first thing, I'll try and answer your question, let me know if this, so the first thing is that, so that Jupiter error bar there, first of all, so that is the measurement from Juno of the oxygen abundance. It's difficult to say whether that is representative of like the bulk oxygen abundance in Jupiter's atmosphere, since it was just a dropped probe in one location. But I think maybe the bigger point that will answer your question is like, why combining like the carbon and oxygen error bar sizes, why is the error bar on Jupiter's C/O ratio so big, and why are the ones on the exoplanets so
Indeed.
small
All,
compared
yes,
to
all of the above, yes.
Yeah, okay, so the one for Jupiter is actually just calculated straight from getting the number for the carbon abundance and the number for the oxygen abundance and dividing those and propagating the error bars. The reason it's much bigger than the ones for the high resolution results is because the way that high resolution data reduction happens, it's often much easier to constrain like relative abundance ratios than like absolute abundances. So that's basically just an artifact of how high-res data processing works, is that the individual like oxygen and carbon abundances look more uncertain, but the ratio is very precise. Does that answer your question at all?
Yeah, I guess the question is the ratio very precise because is this a retrieval analysis or a forward modeling analysis? I guess I'm wondering, I can imagine that the model returns a precise ratio, but one might be skeptical of.
Yeah, so for those two, those were actual high-res detections of like CO and water, and then they literally just took the ratio of the detected abundances. So I don't think those have models looped into them.
When you have a large calibration error, when you take the ratio, that is smaller, but the calibration error could be.
Yeah. Anyway, yeah, so this is kind of just a taste of what we'll be able to start doing with hot Jupiter chemistry with JWST. Any other questions about that before I move on? Yeah, go ahead.
You said it's revolutionizing our understanding. I guess I don't have a good sense of how surprising was the sulfur dioxide photochemistry detection. Are we seeing things that were in all the models and now we can finally observe them, which is great because we can get more detailed measurements, or is it something totally unexpected?
Yeah, so the sulfur dioxide thing is totally expected based on the way photochemistry works in the solar system. That was mostly exciting just because we'd never done that before. But although it was, I guess it's not surprising, like looking back at it, that we would have expected that to be there. When we saw the feature from sulfur dioxide, there were like, a solid week of everyone being like, what is that? What molecule could that be? And then once everyone figured out it was sulfur dioxide, Shami Sai, who wrote the paper on the photochemistry, was like, oh yeah, actually it makes sense that we would predict to see this in a hot Jupiter. Although, it wasn't like, nobody had thought of that before, basically.
Okay.
But it's a like natural extension of like solar system chemistry, I guess. Yeah. All right, so then I also want to briefly talk about a little bit of the results from the secondary eclipse of WST-18b. I'm not going to talk about actually the main results on the secondary eclipse spectrum from this paper. It was just released on arXiv last week, but that was mostly to kind of help people with planning observations with JWST. It was mostly to share the knowledge that the community had about how well the instrument was working. And it's still under review, so since this is a pretty big group, I'm going to avoid talking about most of it since, we're going to talk about that after the paper's been officially accepted. But I do want to quickly mention something I'm really excited about being able to do with JWST, which is eclipse mapping. So the way that this works is, so when we're observing our planet in secondary eclipse, it's going behind our star. And we can actually observe it during ingress when segments of the planet are disappearing behind the star one by one, and then in egress as the planet is slowly reappearing from behind the star. And if we combine that information, we can use that to make a 2D spatial map of the planet's atmosphere. And then with JWST, if we're observing at lots of different wavelengths where we're probing different pressures in the atmosphere, we can actually combine all of that information to get kind of a 3D resolved map of the atmosphere of a hot Jupiter with information in latitude, longitude, and altitude. So something that I was working on for this paper on WST-18b, along with Ryan Challoner, who's at University of Michigan, was doing eclipse mapping of the planet. So this is just showing kind of a first result where we did actually a broadband eclipse map, so it's not resolved in wavelength at all. But this map plot on the right-hand side is what our best fit solution looked like, and there's a color bar down below it. Also, the fading out to white on that color bar indicates essentially where the visibility gets to the point where it's not contributing significantly to the planet's secondary eclipse spectrum, either just because of the viewing angle as you get to the poles, or because as you get to too far away from the substellar point, we're just not seeing that part of the planet in our secondary eclipse observation. And then on the left-hand side here is a trace showing the latitude averaged longitudinal temperature distribution. For the red and blue are two different solutions that fit this data set well, and then it's compared to several GCMs. There are all of the other solid lines. So what we found were there were kind of two different solutions that could fit this planet well. The red one, which is kind of a more standard hotspot model, it peaks near the substellar point. And then the blue one, which alternatively has this kind of extended plateau of relatively constant high temperature near the substellar point. But in both of those cases, we found that the results broadly matched the predictions from GCMs that this planet, which is very hot, would have a temperature distribution that was symmetric around the substellar point in longitude and drops off very quickly in temperature as you get near the limbs of the planet. And we don't have full results yet on this, but Ryan Challoner and I are working on doing spectroscopic eclipse mapping of this planet as well. So this GIF is showing, as you step through different wavelengths in this planet, different temperature maps that we've got out. So there's no error bars on this yet because it's still in progress, but you can kind of see the hotspot changing in size and shifting around and changing in temperature as you go through these different wavelengths. So hopefully we'll have some more cool results on this soon. All right, I guess this is a good place to stop and ask for questions again, because we're going to switch tracks to go to terrestrial planets. Any more? No?
No, you can go ahead here.
All right, perfect. All right, so of course, one of the things that I'm really excited about, and a lot of people are really excited about with JWST, is that we're going to, for the first time, be able to study in detail the atmospheres of terrestrial planets as well. So part of this is just the wavelength region that JWST is sensitive to. So here I plotted black body curves for bodies at a bunch of different temperatures ranging from 300 to 2000 Kelvin. And if we look at the wavelengths that HST observed, they're pretty short wavelengths in the optical to near infrared, which covers the black body peak for temperatures around 1000 to 2000 Kelvin. So Hubble was pretty good at studying these hot Jupiters, which have temperatures around 1000 to 2000 Kelvin, but it really wasn't suited to studying, in particular, habitable terrestrial planets, which are at these much colder temperatures. On the other hand, JWST has wavelength coverage extending all the way out to the mid-infrared to about 28 microns, which means it'll cover the regions of peak flux for bodies that are much cooler, extending down into these habitable temperatures. So JWST is really going to be the first time we have a good ability to study these habitable temperature planets. And in particular, JWST is going to be looking at habitable planets around M-dwarfs. So for several reasons, it's going to be better at looking at M-dwarf planets than planets around sun-like stars. The first is just the distance of the habitable zone from the star. So for a sun-like star like our own, our habitable zone is here at 1 AU, where the orbital period is a year. So if we wanted to look for transits of an Earth-like planet around a sun-like star, we'd have to wait 1 year in between every single transit. On the other hand, for an M-dwarf habitable zone planet, the habitable zone is at about 0.06 AU for an M-dwarf, or an orbital period of about 13 days. So you have much more frequent chances to catch that planet transiting. Also, because the habitable zone is closer in around an M-dwarf star, the probability of finding a planet transiting in the habitable zone is much bigger. And that's because in order to see that transit, the planet has to have a very narrow range of inclinations so that from our perspective, it actually crosses the disk of the star. So for a sun-like star, the probability of finding a planet transiting in the habitable zone is only about 0.5%, but that probability is 4 times higher for an M-dwarf. And then finally, because M dwarfs are smaller, the signal size that we see in transit is just much bigger for an M dwarf than for a sun-like star. It's just a lot easier to see a small rocky planet going in front of a small M dwarf than in front of a big sun-like star. But we have a lot of questions about how habitable zone planets around M dwarfs might actually be. In particular, one big question I'm going to focus on today is that we know M dwarfs are much more active than sun-like stars, and particularly in their early lives, they have a high level of activity and lots of high energy flares. And it's possible that that activity could strip atmospheres off of small rocky planets before they even have a chance to form life. So kind of one of the big first order questions we want to answer with JWST is whether planets in the habitable zones of M dwarfs can even hold on to atmospheres long enough for life to develop. So we can look for atmospheres on these planets using any of those three methods I talked about earlier. So just going back through those real quickly again, first is primary transit. We can look for the starlight being filtered through the atmosphere and look for the molecular features that indicate that we've seen a planet's atmosphere. So this is just showing one example of how that might work for the habitable zone planet TRAPPIST-1e with one of the instruments on JWST. And you can see all those detections of CO2 and water and ozone and molecules that would indicate that we have seen an atmosphere here. But the problem with looking for atmospheres in transit is that it can take a lot of stacked transits to build up the sensitivity to see these really small molecular absorption features. And also clouds can block out the signal, so we may not even see anything. And if we observe a flat line in transit, we actually have no way of differentiating. Is that because we are seeing a planet that doesn't have an atmosphere? Are we seeing a planet that has an atmosphere, but it's totally cloudy, so we can't see anything? Or are we seeing a planet that has an atmosphere, but the molecular features are so small that it's below the level of our sensitivity? So just a couple weeks ago at JWST, there was actually a big press release showing this transmission spectrum of one of the first rocky planets that was observed by JWST. So this is a planet a little hotter than habitable, orbiting an M dwarf star. They observed two different transits. It's a little hard to see this spectrum with the way the screen is here, but essentially they saw a spectrum consistent with a flat line. So they were able to rule out atmospheres that are hydrogen-dominated or clear methane-dominated atmospheres, but they found that there are a lot of other compositions that are still consistent with their observations, like cloudy methane-dominated atmospheres, water-dominated atmospheres, many other things that are below the level of the sensitivity of these data. All right, so then we can also observe planets in phase curves where we see their thermal emission going through an entire orbit of the planet. So this has been done actually with a couple rocky planets with the Spitzer Space Telescope now. So this is showing one example for the planet LHS 3844b. So the expectation for these planets, since they're tidally locked, is that if you don't have an atmosphere, the day side will be very hot and the night side will be very cold. And then if you do have an atmosphere, it can redistribute heat around the planet. So here you can see that they've got this very large phase curve amplitude, which indicates that this planet at least doesn't have a very thick atmosphere because it isn't able to redistribute heat significantly. But the problem with phase curves is, like I said earlier, they take a long time to observe. For habitable zone planets around M dwarfs, they can take a few days, maybe even up to 10 days. So we really want to make sure that we're using the resource of JWST as efficiently as possible, and these phase curves just take a very long time to get an answer. So what I'm going to be talking about today is using secondary eclipse photometry to look at these planets and determine whether they have an atmosphere. So I'm going to be talking about doing observations with JWST's MIRI instrument using the low resolution spectrograph. So that actually produces a spectrum from about 5 to 14 microns. But for this secondary eclipse photometry technique, we actually sum up all of that light into one broadband secondary eclipse. So what we're essentially measuring is a broadband temperature of the day side of this planet. All right, so if our planet doesn't have an atmosphere, we expect, as I said earlier, that it will have a hot day side, and that's because it's getting all the radiation from the sun only on the day side, and the night side stays very cold, and without an atmosphere, it doesn't have a good way to spread that heat out. And then if we add an atmosphere on top of that planet, that will decrease the secondary eclipse depth or make the day side colder in one of two ways. The first is that a thick enough atmosphere can transport heat around to the night side. So here I'm showing some models of phase curves for a couple different terrestrial planets. The black dotted line on all of these is a planet that's just a bare rock. So for all of those, you can see that the day side, which is at a phase of about 0.5, is very, very hot, and the night side at a phase of 0 and 1 is very cold. And then as you add a thicker and thicker atmosphere on top of these bare rock planets, which are the lines going from blue to yellow there, you can see that as the atmosphere gets thicker and thicker, you progressively cool down the day side and warm up the night side because that heat is able to more effectively be redistributed around the planet. And then these black points on the sides of each of these plots are the expected size of error bars you'd get on a day-side temperature measurement from a single observation with JWST. So you can see that once you get to a pressure of about a bar or thicker, the atmosphere begins to redistribute heat effectively enough that you can tell the difference between that cooler temperature indicating you have an atmosphere and the hotter temperature indicating it's a bare rock. All right, so one way that an atmosphere makes the day side colder is through transporting heat around to the night side. Then the second way an atmosphere can make the day side colder is that it can have high albedo clouds or hazes. So this plot is showing the expected albedo from clouds made of different particles with particle radius on the x-axis and the cloud column mass on the y-axis. And to kind of guide your eye, the stars here indicate typical cloud parameters for Earth, Mars, and for the high altitude hazes that form in the upper layers of Venus's atmosphere. So depending on your cloud composition, if you have an atmosphere that has clouds with a very high albedo in it, that will also reflect away a lot of light on the day side of the planet, which will also effectively cool down the day side temperature that you measure. All right, so then combining all of this information, kind of our working hypothesis for what you'd be able to see when you look at a rocky planet in secondary eclipse with JWST, is that we expect that bare rocks will be very hot, so there's a minimum temperature or a minimum secondary eclipse depth that will be consistent with a planet being a bare rock. And then if you observe a secondary eclipse depth that's significantly lower than that, you observe a lower temperature, then your planet must have an atmosphere. But one complication to this is that I said one of the things that can cool down the day side is by having a high albedo atmosphere, high albedo clouds that reflect away light and cool down your planet. And you could get a similar cooling effect by having a very high albedo surface. So how could we tell the difference between a high albedo surface and an atmosphere? On Earth, of course, we know of a lot of high albedo surfaces that we could easily confuse with reflective clouds in the atmosphere if we were looking at our planet from very far away. We've got things like snowpack, and then rocks like limestone, which makes the White Cliffs of Dover, and granites like this one, which is from Yosemite. And all of these would be very confusing for us to tell the difference between one of these surfaces or an atmosphere with high albedo clouds. So what we did is we looked at spectra of all the different mineral types that commonly make up the surfaces of rocky bodies in the solar system. And we looked at what albedos each of these surfaces have when we put them on a planet around an M-dwarf to see how well we could tell the difference between a high albedo surface and an atmosphere and in what conditions we'd be able to make that distinction. So here all these solid lines are showing all of these different reflectance spectra for different mineral types. And we found that these kind of divide into two categories. So the first ones, the red colored lines here, are ones that are all relatively low albedo surfaces. So these ones, if we saw them, we wouldn't easily confuse them with an atmosphere on a planet. And then the blue ones are the ones that are high albedo and would cause us some concern because we wouldn't be able to differentiate between a planet with that high albedo surface and a planet with an atmosphere. However, it turns out for various reasons, we don't expect any of these surfaces to exist on a hot rocky planet, one that's hotter than the temperature of the runaway greenhouse limit. For most of these, that's because these minerals require water. So clays require water to form, granites have water incorporated into the mineral structure, so we wouldn't expect any of those surfaces to form on a planet that's hotter than the runaway greenhouse limit because there wouldn't be any water around for those surfaces to exist. So based on that, we figured out that there's essentially a temperature range where we can say for sure that we wouldn't get confused between a high albedo surface and an atmosphere on a planet. So if we look at planets that are too cold, colder than the runaway greenhouse limit, these high albedo surfaces like granites could exist, and we might not be able to tell the difference between a planet with a high albedo surface and a planet with an atmosphere. If we go hotter than the runaway greenhouse limit, which in this paper we conservatively set at a substellar temperature of 410 Kelvin, then the only surfaces that we expect to exist are all very low albedo. So in this case, if we observe a cold secondary eclipse temperature, we can definitely say that that has to be due to an atmosphere.
What is ultramafic?
Ultramafic, yeah. So that's the like thick red line here.
Oh yeah. What is that?
Yeah. Okay. So it's not a rock composition that we really have on Earth, but it's like, okay. So on Earth we have felsic and we have mafic rocks. Hypothetically, depending on the environment in which you form mafic rocks, you could get rocks that are more mafic than what we have on Earth. We don't have them, but like it would make sense for them to form in the wild, I guess. So. Yeah, they're a possibility for what we could see on other planets.
Oh, sorry.
Yeah.
So the formation history of those minerals could be related to having those planets in, far away from the star, maybe where they could have water, and then you can have some migration process or so. So
yeah,
is that consistent with also? You say that if the temperature now is beyond the greenhouse runaway temperature, then it's unlikely those minerals exist, but they could have formed, and you have during the formation history of those planets.
Yeah, that's a good point. Yeah, so if you took a planet that was like all granite and you stuck it interior to the runaway greenhouse and you left it there for billions of years, actually it does all of the volatiles get dissolved out of the surface. I'm forgetting the correct word for that. So it does lose its volatiles. So we are kind of implicitly assuming here that these planets have been in their current orbits for billion-year timescales, and none of them are recent arrivals. But yeah.
Yeah, thank you.
Mm-hmm.
Do you also include, for example, collisions between planets?
Yeah. So I guess I think we're mostly considering mature planets that haven't really had anything happening to them recently. So no major collisions, no recent migration. We're kind of assuming that all of these planets are in relatively mature systems. Yeah. But that would probably also mess things up. Okay, so so in this temperature range where we would predict low albedo surfaces, then we can say that a measurement of a cold temperature indicates the presence of an atmosphere. And then it actually turns out that when we go to hot enough planets, this assumption also starts to break down. So once we get to a substellar temperature above about 1250 Kelvin, we actually start to get partial devolatilization of the rock, where the rock itself starts to vaporize, and the first components to come out of the rock are the more volatile things. So what that leaves behind on the surface of the planet are less volatile compounds like corundum, or rubies and sapphires. And it turns out that raw rubies and sapphires are also very high albedo. So while you might be interested to go harvest the day side of a planet that's entirely covered in sapphire, I'd certainly be interested to see that. You wouldn't be able to tell the difference between a high albedo corundum surface and the presence of an atmosphere. So that's kind of an overview of this technique. So I'm really excited that we're actually going to get a chance to test this out this year with JWST observations. So coming this summer, I'm going to be observing 2 secondary eclipses of the hot rocky planet GL486b. And with those 2 secondary eclipses, we predict that we should be able to differentiate between a bare rock and the presence of an atmosphere at about a 5 sigma significance. And then, of course, this whole time I've just been talking about these data as if we're measuring one broadband photometric temperature. But the exciting thing about using MIRI's LRS instrument is that we actually are getting spectra. So if we do detect the presence of an atmosphere on this planet, we can divide that back up into its spectrum and look for atmospheric features that would indicate different gases to tell us whether this planet has perhaps an Earth-like atmosphere or a Venus-like atmosphere or a water or CO2 rich or anything like that. So we can do kind of the same science you can do in transmission and try and look for some of these spectral features. But that's not actually the only thing we can do with these spectra. So if we detect that the planet doesn't have an atmosphere, then we'll actually be sensing emission from the surface of the planet itself. So we can actually look for mineralogical features to tell us the composition of the rocks on the surface of the planet. So this will be the first time that we'll actually be able to do what I like to call exogeology or exomineralogy and try and tell whether the solid surfaces of terrestrial planets outside our solar system are similar to what we observe in our own system. And kind of more broadly, this technique can give us kind of a statistical understanding of the influence of M-dwarfs on atmospheric loss and terrestrial planet habitability. So in this plot, I'm showing all of the known rocky planets with those orange dots sorted by their equilibrium temperature on the x-axis and the eclipse spectroscopy metric on the y-axis, which essentially tells you how good of a target these planets are for observing in secondary eclipse. And everything above that gray shaded line is a good enough target that we expect that in a single secondary eclipse, we would be able to tell the difference between a planet that does or does not have an atmosphere using this technique. So this is really a quick way to build up an understanding of where atmospheres exist on what types of orbits around what types of stars, and can kind of give us a more holistic understanding of how the activity of M-dwarfs impacts their ability to host habitable planets. Now, I also drew on this plot in blue the habitable zone. So I do want to note that if you were listening carefully earlier, you'll notice I said this technique only works at planets that are within the runaway greenhouse limit, because otherwise we could have those high albedo surfaces existing that would confuse our interpretation of the secondary eclipse temperature. And the runaway greenhouse limit is, by definition, the inner edge of the habitable zone, because we define the habitable zone as where we could have surface water. So this technique doesn't work for looking for atmospheres on habitable planets. But if we study the planets interior to the habitable zone, that can still teach us something about how habitable we expect planets around M-dwarfs to really be. For example, if we see that atmospheres are common on planets interior to the habitable zone, then we can expect perhaps that maybe all planets in the habitable zone would also be able to retain atmospheres. So before I end, I just want to acknowledge all of my co-Is on this project, in particular Daniel Cole and Mathieu Malik, who along with myself developed this secondary eclipse photometry technique. I also want to acknowledge the whole JWST Transiting Exoplanet Early Release Science team, as well as funding from my NASA Sagan Fellowship. And then I'd like to respectfully acknowledge that we're gathered on the land of Indigenous peoples today, and knowing where we live and work as astronomers can't change our past relationships, but that an understanding of that colonial history can inform the direction we go in the future. All right, so just to conclude, this secondary eclipse photometry method is an efficient method to detect atmospheres on terrestrial planets orbiting M-dwarfs. And that's because those atmospheres will decrease the secondary eclipse depth, either through transporting heat to the night side or through hosting high albedo clouds. And we can unambiguously identify the presence of an atmosphere for planets with substellar temperatures between about 410 and 1250 Kelvin. And we're going to be doing this method for real with JWST data coming this year. So I hope you look forward to seeing those results as much as I am. Thanks, and I'd be happy to take any more questions.
Any question? Yes, Tingshan.
Yeah, I'm curious about you said like if we found a high albedo on this kind of planets, we can infer that those are identified as atmosphere. But what if an atmosphere without any cloud on it? It's just we couldn't have any detections in the end, or we can still measure the curve and see whether we have the atmosphere.
Yeah, so if you have an atmosphere that's like totally cloud-free and it's thicker than about a bar, you should still be able to measure it just by measuring the secondary eclipse depth. Because if it's thick enough to transport heat to the night side, then that'll still cool the day side off because that heat gets shifted around. You wouldn't be able to detect a thinner atmosphere than that if it's totally cloud-free. So there is kind of like like lower limit on the pressure that you'd be able to detect surface pressure, but yeah.
Let me first go to Andrew. Andrew raise hand first, and then I will go to you guys. Andrew?
Yeah. Thanks for the great talk and overview, Megan. So I thought especially interesting, I guess, that 1 bar seems to be the interesting level of atmosphere that redistributes temperature. I was wondering if maybe it's something you made for your proposals already, like what would Earth look like with this type of secondary eclipse observation, maybe with enhanced signal to noise?
Yeah, so actually that gray line on this plot is a 1 bar Earth-like atmosphere plopped on GL486b. So that's what it would look. So you are able to like distinguish that in the like photometry sense. You're able to distinguish it from a planet with no atmosphere. And then you can kind of try and get, well, I guess I'm pointing at the screen, you're on Zoom. You can kind of get some of these spectral features that you can start to look for. So you might be able to, I think what you'd be able to do with this technique is maybe identify 1 or 2 major components of the atmosphere, like CO2 or water, things like that. You won't be able to get, a detailed composition just from a couple secondary eclipses. You'd have to follow that up.
But I guess like for your method of like, detection of atmosphere by comparison to bare rock, I guess what would the level of bare rock be up here?
Oh, so yeah, I guess I don't have them all on the same one, do I? But I guess you can kind of by eye compare here. So like the bare rocks are generally hotter. So whoops.
Yeah.
Sorry, it's hard to. Yeah, so you can see like a lot of the atmospheres, if you kind of average the secondary eclipse depth in this range, it's probably around like 75 or 80, and the bare rocks are like 100.
Okay.
Yeah.
And then the atmosphere result, I mean, I know certainly for hot Jupiters, right, the extent to which an atmosphere redistributes temperature is, dependent on various things. So how much is the atmosphere result dependent on things like GCM modeling results and whatnot?
Yeah, that's a good question. So if you go look at, so Daniel Cole had a paper on this. It was actually, I think it was originally in the same grouping as, so all these papers were published in 2019, but I think it actually didn't get published until like 2022 or something. It was like a single author paper by Daniel Cole, where he essentially ran GCMs with a bunch of different atmospheric compositions to try and get a scaling for the heat redistribution. And it ended up depending on like the long wavelength opacity and the pressure, but like ended up being a similar-ish scaling for the different atmospheric compositions he looked at, which were kind of similar to the ones I showed, like one that's CO2 rich and one that's water rich and things like that. But you can go look at his paper if you want more details on that.
Oh, thanks.
Yeah.
In the plot you had showing the 3 different sources with the day-night contrast as a function of different amounts of atmosphere, it was the curves over.
Oh, this one?
Yeah, that one.
Okay.
So it seems like the error bars you're able to measure drop as the contrast drops. Is there a physical reason for that, or is it just that you picked 3 planets to demonstrate that?
That's a good question. Yeah, so I have an idea. I don't know if this is going to be right, but I'll share it with you. So essentially, as you go from left to right on this plot, you're going up in equilibrium temperature, which is why the error bar is dropping. The error bar to first order just depends on the temperature of the planet, because that's how much flux you're able to get from it. And then, like, my guess would be that it essentially the like percentage difference from going from a bare rock to a like however much atmosphere is approximately the same, but like a 1% difference on a body that's like 1,000 degrees versus a 1% difference on a body that's 500 degrees is different, like absolute ability to tell the temperatures apart. So I'm not 100% sure if that's it, but yeah, I think like basically TRAPPIST-1b is the coldest and LHS 3844b is the warmest, and that would be my guess. It has something to do with that.
Thanks.
Kitty.
Go ahead.
Oh,
I've
okay.
already talked.
Because this was just based on this plot. I'm just wondering, is part of that was coming up just based on the different y-axis for the last one?
Yeah, that's a good point. Yeah.
Yeah, that's right.
And then on top of that, then because my original question was before this was, so what do we know what determines the difference between the day and the night side differences? So like the day side, or the center of the phase curve has a certain difference. We got like 40 parts per million for the night side for TRAPPIST-1b, but like 200 parts per million for LHS 3844. Is that just straight from the temperature again, or?
Yeah. So that's again, it's essentially this. So there's this scaling that Daniel Cole produced from his GCMs that is like the amount of heat redistribution you get is proportional to several things, and one of the things it depends on is pressure. And so I think that's like the fraction of heat that's getting redistributed is approximately the same for a 1 bar atmosphere on everything. And then the net amount of energy that's coming in is different because they're all at different equilibrium temperatures. Yeah. Yeah.
Okay, Kathleen.
Yeah, I'm just wondering about the composition of the atmospheres when we're going to 2,500 Kelvin. And so is 2,500 Kelvin the upper limit of atmospheric retention for anything? Like I would expect there's some point at which you're not going to retain anything plausible. And then the ability to extrapolate well below, to interesting things about habitable zone planets surely depends on the composition.
Yeah. So that's actually an interesting question, and something we're interested in looking at as well is like the ability to retain atmospheres on these really hot, like whether you can, I mean, at some point, like when you get to that like 1200 Kelvin where the rock starts to vaporize, you're probably not at all talking about like carbon, oxygen, nitrogen based atmospheres at all. It's like rock vapor atmospheres. Yeah. So yeah, everything kind of stops being in the same regime at some point around there, but we don't actually know, I think, exactly where that transition to like not being able to hold on to any volatile atmosphere.
But I guess, but the plot that you show going out to 2,500 Kelvin, I guess, like that's, what does it mean to have? What does it mean to have an atmosphere, right? Beyond, so most of that, a lot of that plot is well beyond this. So just what does it mean to have an atmosphere out there?
Okay, yeah, so first of all, I did a horrible thing and changed temperature axes. This is an equilibrium temperature now, not substellar temperature, so probably like 1,500 is a bit more of like where but you're right that a lot of these are so hot that we might expect maybe like a magma planet or a rock vapor atmosphere and like nothing else, so yeah.
So the range of extrapolation is probably below.
Yeah, it's probably around the
15,
like 500 to 1,500 equilibrium temperature here. Yeah.
Okay, next question, Everett.
Excellent talk, Megan. I was just wondering if I guess I haven't caught up on the literature on what the latest atmospheric escape and mass loss models say about these planets. Is there any agreement that they lose their atmospheres around late M dwarfs, or they keep them, or it's just totally unknown?
Yeah, I don't know for sure. I was literally just today actually looking at a paper that I'll stop sharing my screen so I can look it up. Hold on. And then I can tell you the author. Nakayama is the first author. It just was posted on the archive like a few months ago, and essentially it was talking about how like planets with like nitrogen, oxygen, Earth-like atmospheres can have a lot of like atomic line cooling, which can actually help them retain atmospheres in the face of like heavy XUV irradiation. So essentially I'd say it's still up for debate. Like there's still papers actively being published saying like, oh, these planets like would be able to retain atmospheres for a while or would not, depending on how they interact with the like star. So yeah.
Okay, thank you.
Okay, any other question? Okay, I have just a random question. So how many like Earth-like planets, is there any your plan of observing Earth-like planets, and then what's the plan for the future with JWST?
Like how many
Earth-like planets are being planned or to be
Yeah, so I think I guess so in terms of secondary eclipse observations, I think there's something it's not many, maybe 5 that are currently planned. There's a big program doing transits, which is the one that I showed that one result from. And I think they've got, I don't remember, closer to of order 10 planets, but Sarah Moran's actually involved in that program.
Okay,
so
Sarah's
you
not
can
here
ask her.
today,
Yeah.
but
yeah.
Catch up with Sarah.
Yeah.
Okay, so if there isn't any other question, then I would like to say good luck to your JWST proposals, and thank you very much for Megan giving this talk while crazily writing proposal.
Deadline for proposal.
Friday.